welcome to episode 24 of Defen with Ray in Belgium.
And Vijay from Holland.
And Dragan from Belgrade.
So, Dragan Juric, yes?
Yes.
Have I got your name right, Dragan?
Yeah, well, almost perfectly. Not quite, but it's good.
See if you can do it any better then.
No,
Dragan Juric.
No, it's Dragan Juric.
Dragan Juric. Okay, so I think it's this episode we're basically trying to pronounce his name. We just keep repeating it.
Yeah. Let's try it. Where is it going wrong? So Dragan Juric.
No, it's Dragan, like R.
Dragan.
Yes, something like that.
Okay, Dragan Juric.
Yeah, Juric. It's
Juric.
Yeah, it's Juric.
No, it's okay because it's a bit like Dutch. Dragan Juric.
Almost perfect.
I'm just gonna call you with your GitHub username Blueberry.
Yeah.
Or that's
that's pure racism, VJ. We're not having that. Come on. We're gonna call you Blueberry. Right, from now on, hello Blueberry.
Hey, he's the guy who picked his name, so I'm not discriminating against any other berries.
Yes, but Blueberry is Belgian comic book anti-hero. So Ray as a Belgian guy should know who Blueberry is.
Well, I'm kind of I'm just being integrated, let's say, Dragan.
But
so
maybe it's going to be on the test. So
I've already taken the test. It wasn't there. And I got away with it. Yeah, but it's quite funny that your name is so complicated, yet your library. Well, it's not complicated, but it is to our tongues. But your libraries are uncomplicated. So maybe we'll move on to that.
Yeah,
but before we do that, we need a little bit of introductory, a little bit of chat just to warm everyone up. So we were talking beforehand about the fact that Mac is like very popular amongst developers, but you prefer the Linux desktop. So, and I notice at work there's a lot of people using Linux desktops, and I notice with very many people in the Clojure community now, these Linuxes are coming to the fore. So, is 2017 the year of Linux desktop for Clojure?
Well, I'm not sure because I'm not using desktop.
Oh my God! You're definitely splitting hairs now.
No, I'm using Linux without the desktop. So
what? Wait, you're just going blind, are you?
No.
No monitor.
No, I'm using Emacs with Xmonad and shell.
There you go.
So no need for desktop.
Yeah.
And I don't have a mouse on my computer.
Yeah, so that makes more sense. Now we're
talking.
I
see.
So
right,
everything is on the keyboard and Magic Trackpad or whatever it's called for scrolling on Google Chrome. So basically, for all my developers and development environment and everything else I do, I can do it with shortcuts on my keyboard.
So basically, what you need is you need a 3270 into some kind of Google backend or something. That's all you need.
I don't even know what that is.
Well, it's like an old IBM terminal, IBM 3270.
Yeah, okay, probably before I was born.
Well, at least it's not like you're not using it like RMS does, right? Because if he wants to read web pages, he'll send a request to a server, and then the web page is sent as an email to him.
No, I have a GUI, I have a Google Chromium, I have VLC, I watch movies and everything else.
Okay.
I just don't have a desktop, so no taskbar, no mousey stuff. But I have Xmonad. It's like a tiling window manager. So
I know Xmonad is written in Haskell, right? I mean, you need to.
But I don't use it because it's written in Haskell. Because
of course, but
I just set it up 5 years ago, and I haven't touched it since then. So it just works.
So now we know what to use.
Has it had any side effects?
Yes, side effects. It works. That's one side effect. So I'm not even a fan of Haskell. So
we'll get there slowly. So can you give us some? Okay, we talked about your setup already, which is fascinating, and I think this is the first time when we had someone like someone with this kind of setup. So can you give us a bit of a background on where do you work and how do you get into Clojure? What do you do usually? I mean, I'm guessing most of the time you're configuring Xmonad, but rest of the time, what do you do?
Um, I had some problems in communication here, so
Oh, sorry.
I missed half of the question, but I'll try
It's
to answer
okay.
it. So,
Well, I think what we should do is we should just chop it up into like 5 questions rather than one big long one.
yeah.
Yes.
Because internet is a bit choppy. I think connection is a bit not great. But okay, how I got into Clojure, right? That's the question.
Yeah.
So it was in 2009, and for some time before that, I was trying to find some solution that will give me meta programming facilities for some stuff that I needed to do. And I was trying with Aspect J and some complicated Java stuff and everything, but it was clunky and required lots of boilerplate and everything. And then Clojure was, I think, released or about to be released. So it's maybe May or April of 2009. And I was looking into this before, but not really into detail because it was not quite practical because of the lack of libraries or ecosystem or I just didn't know how to use it properly. So when Clojure appeared, it clicked immediately. And fortunately, because I work at university, I can choose my own technology and what I do and how to do it. So it was an easy switch. I don't have VJ's problems of like having to code in Scala. So.
Yeah.
So I switched immediately, and well, it was quite an easy ride since then. So I'm quite satisfied with what Clojure offers. It has its rough edges or so, but it's manageable.
Yeah, it's interesting that because you're doing the Clojure stuff, but you're very focused on performance. So what was that story? Because I think you've been in some of your talks, you've talked about the JVM and sort of lower level libraries, but what do you think about like the JVM ecosystem for Clojure? Is that something attracted you, or was it just the language itself? Then you figured you could get underneath it?
Well, actually, when I started doing Clojure, I was not into high performance stuff. So,
right, okay.
So at that time, I was more like domain modeling, something doing with ontologies or modeling domains, some constraints or so. And at that time, so JVM wasn't a problem. On the opposite, it's quite performant for that kind of stuff. But later, when I started looking more into machine learning, I realized that, well, JVM and similar environments are not performant enough because especially machine learning technologies that I'm interested in are quite computationally expensive. So really expensive, like billions of operations are needed.
Can you give us an example of that kind of thing?
Well, the example, the most obvious example is Markov chain Monte Carlo sampling that I mentioned at Euroclosure. So basically, the point with this kind of sampling is you're exploring a hyperspace. Hyperspace is a space with more than 3 dimensions, let's say. So you have space with like 50 or 100 dimensions, and each dimension is continuous. So infinite numbers of possibilities. And in machine learning, there is a thing called the curse of dimensionality. So basically, if you have some method and in one dimension, you can say, okay, I will sample really finely that one dimension. So I need maybe 1,000 points. But in these 1,000 points, I will be able to discover the shape, rough shape of the function. in 1 dimension. In 2 dimensions, I have to check 1,000 times 1,000, a million points. In 3 dimensions, in times 1,000, it's a billion points. In 100 dimensions, it's like 1,000 to 100. So it's really, by brute force, you cannot compute it at all, like in million years. So basically, all these methods try to somehow reduce the space, to randomly search the space, but not so randomly. So a lot of computation is needed, but these computations are numerical, so not much logic, more like millions of computations of functions like exponent and sinus and cosinus and something like that, combinations of those. Basically, the point is that GPUs are really suited for such kind of computations, and lots faster than CPUs. And Java is well, it doesn't have access to hardware facilities even of CPUs, not to talk about GPUs. But even on the CPUs, you have many hardware facilities that can be used, like pipelining or AVX instructions and SSE instructions and such things that can be used with numerical computations and give speed up of 10 times or 20 times or 50 times if programmed well. So Java doesn't have access to that. So basically, that got me interested. I need performance for a low price, because I'm not Google or Microsoft. I cannot have like huge data centers and just throw so much computation on it. So I really need to be like optimal. So get as much as I can from the cheap hardware. And that's how I got into researching how can I do this practically, but from Clojure, because I love Clojure. So I love programming in Clojure.
So the libraries...
Did you look at... Sorry, go on, Vijay.
Sorry. So I was looking at the libraries that you built so far for essentially for utilizing the GPUs. So you have, of course, Neanderthal, that is the matrix library, and you have Clojure CL. So can you give us some idea about what each of these libraries do and what are they used for? Because I see one of it as a much more lower level library than the other one. So
and there is a third library, Clojure CUDA.
Clojure CUDA. Yeah, this is for NVIDIA, right? Yeah.
So what is the purpose of all this? Basically, when you develop such kind of software, like numerical software, and you need access to all these low-level facilities, the point is that you need to basically the way that you program it is similar to Clojure. If you understand the map and reduce, basically you understand basic stuff of how these massively parallel computation is done. So Clojure is a good approximation of what these libraries do, but what Clojure cannot do is cannot access the real hardware stuff. So it cannot tell the GPU what to do, because it doesn't have any connection to it. So basically, let's start from Neanderthal, because it's probably something that most users would try first.
Yeah.
So what Neanderthal enables you is to create some structured data, like vectors and matrices. So basically blocks of data that you want to compute. And then call some standard functions that are optimized for running on different kinds of hardware. So you as a user have to be aware that where it computes and what does it need to compute, but you don't have to do it yourself. Neanderthal will do this for you. You just have to call it, like matrix multiplication or matrix factoring, or like solving systems of linear equations or something like that. Also, what Neanderthal does, it says, okay, you can do your computation either on the CPU, like your processor of your computer or laptop or desktop or whatever you have, or you can send it to the GPU for computations. Now, GPU can be AMD or NVIDIA or something else, but probably NVIDIA or maybe AMD.
Yeah. Yeah.
So NVIDIA has its own environment, which is CUDA, right?
Yeah.
So basically, you call NVIDIA's CUDA driver and says, okay, do this for me, like send this kernel. Kernel is a small, like, chunk of code that computes in parallel.
Yeah.
So Clojure CUDA enables you to write your own kernels and call them on your GPU on a really low level. So for Neanderthal, you don't need to use Clojure CUDA or Clojure CL. Neanderthal does this for you. You just have to say, okay, I need this on my CUDA GPU. But it will get you only so far, because most of us write some custom software, like 100% custom or like 19% custom. But each of us needs some custom stuff. So basically, Neanderthal is not enough. It's good for start, but if you really want to use some great software and that other people don't have, and like be better than competition, typically you will need to write some custom algorithms. So basically, Clojure CUDA and Clojure CL enable you to write your own low-level code that runs on the GPU by using Clojure. So you write small chunks of C, like really small kernels of C. All management is in Clojure. Everything is host and management and calling these kernels and everything else, setting up memory is in Clojure. And another benefit is that you don't have to compile anything. So basically, you just run, you fire up your REPL, Clojure REPL, and from the REPL, you have access to Neanderthal, you have access to Clojure CUDA, you have access to Clojure CL. You just provide those strings or files with kernels, provide some Clojure code that manages it, and you just can experiment in REPL. So that's the main benefit.
How do you see so how do you see the role of these libraries in the larger ecosystem? Because these days, I'm pretty sure you know about Clartex as well, right? The Clojure machine learning, deep learning library. So
you mean Cortex or?
Yeah, Cortex.
Yeah, Cortex, right?
So how do you see using these libraries with computations that are related to deep learning stuff? Is there any relation between them, or do you think it's a possible?
Yeah, well, I have a look of Cortex, but basically I'm not so interested in deep learning, because deep learning is really popular now and everyone is interested in it. But deep learning, it's more used for perception. Like if you have pictures or sound or such kind of information, and you need to process it, like classify it or do some recognizing there or so. But I'm more interested in the methods for analyzing data. For example, typical Clojure company will probably collect data about users, how they browse some products, or how they do some transactions, or how they do stuff. So I'm more interested in data analysis methods, like logical stuff, Bayesian stuff. So I'm not so well informed about deep learning. Of course, I know the basics, but I haven't tried Cortex. Now, how would you use Neanderthal with such libraries? How does it fit? Well, Neanderthal is a more general library. So basically, you would use it in machine learning or in physics or any other area that needs numerical computations. And of course, you can build your own deep learning stuff on top of it. Maybe I will provide some libraries in the future, like based on QDNN. Cortex is like specialized matrix, not matrix, but deep learning library.
Yeah.
So basically, now you probably cannot. I mean, you can transfer data from Cortex to Neanderthal and vice versa, of course, but there is no some deeper integration now because Cortex used, I think, the Java ND4J for accessing CUDA QDNN. So basically, they use the Java interop for that. Yeah, Ray.
Yeah, I think maybe it's more interesting to some extent to talk about things we can do with it rather than the things we can't. I noticed one of the things I was looking at your blog actually, and I noticed that in March you released 0.9 of Neanderthal. And you said in that one that it's your kind of your notion of what it needs to do high performance in Clojure is beginning to take shape. Mm-hmm. Maybe we can talk a little bit about that because you said that you started to use Intel's math kernel library. Mm-hmm. And that seems like an interesting concept. You moved from an open source library to this closed source library, but you say it's a good, an improvement. What's the story there?
Well, I've noticed it was obvious that many Clojure users have had trouble installing Atlas.
Right.
Because the point with Atlas is it's built in such a way that you have to build it on your own machine to optimize it, to allow it to choose the best performing kernel for that particular hardware.
Maybe you can just back up a little bit and explain what Atlas is a little bit.
Atlas is...
I think we missed that, actually.
Yeah. Atlas is an open source matrix computation library. So basically, if you are aware that BLAS and LAPACK are standards for matrix computation, numerical matrix computations, like really low level stuff.
Yeah.
So...
these are the linear algebra libraries,
yes.
aren't they?
Basically, BLAS is for primitive operations, and then LAPACK builds on top of it for solvers and such stuff. So Atlas is an open source library for that. So it's quite a good library, and it's open source, so it's really a good choice. But the point is, it's built in such a way that you have to build it on your own machine. And of course, you can use the builds provided by your Linux distributions, for example. But in that case, some distributions don't build it properly. Some distributions package it in such a way that it's not really always obvious how to use it. And so any competent Linux user wouldn't have a problem building it, because it's like some make script with auto tools. And so basically it's not something really complicated, but most Clojure users don't have experience with that. So they have kind of,
it's a barrier to entry, maybe.
Yeah, it's not a fear, but they're not really confident trying it out. So I realized one thing is it's really a problem. It's not a problem for me, but it's a problem for a lot of users. So I like to help them also. But another thing that is also quite important is that Intel MKL is even more performant than Atlas. And what is even more important is that it supports some really important stuff that Atlas doesn't have, such, for example, sparse matrices. And the point with sparse matrices is that the only really good open source implementation is GPL, so it doesn't fit into the Clojure ecosystem.
Yeah.
Right.
So basically, switch to MKL enables two things: easier installation and distribution later, and some features that are not possible with Atlas. So
maybe it's just to help us out a little bit here. I don't know. Is Atlas like? I know that like AMD do things on top of, like, they conform to a lot of Intel standards. Is this something which is only specific for Intel, or does it also run on AMD chips?
No, it runs on AMD processors also. But Intel says that they say it's optimized for Intel processors. So probably it runs better on Intel processors than on AMD's. But I did some search on the internet, and people claim that even on AMD processors, MKL is the most performant library.
Okay.
So I think the only downside is that it's not open source, but it is free to distribute. So it is not a free software, and it's closed source. But you can distribute it with your software for free. So
that's cool.
And it was since the last year. So before that, it required license for such things, but now it's free to distribute.
So basically, you've got like a Clojure library with this Intel core that you can use for this, let's say, classic linear algebra problems. So in terms of like use cases, have you worked up any use cases like the traveling salesman type use cases or optimization type things?
Mm-hmm. Well, the thing is, I use it for Bayesian computations. So it's my use case. It's quite demanding, and I use it a lot. So it helped me tremendously. But maybe to wrap it up, how it can be useful for Clojure programmers. So that I think most people would be not interested in the details so much, but how can it help me, or what can I do with it?
Yeah.
So basically, there are a few things. First, it gives you access to all hardware resources for numerical computations on your machine. So CPU and GPU to the full speed from Clojure. So that's the first thing. Another thing is it gives you an easy connection to the world outside JVM. So I made it in such a way that there is practically no coping costs to transfer your data outside of the JVM. So, for example, if you have some C library, maybe that library doesn't have anything with linear algebra. It just needs some vectorized data to be sent to it.
So do you mean to say that this, for example, this can be used in tandem with something like TensorFlow?
To the extent that TensorFlow can receive primitive arrays, yeah. But I think TensorFlow is a C++ software, so it's a more complicated story.
Well, how about things like computer vision, that kind of stuff?
I suppose, yeah. The point is, it doesn't care. So most of the there are two kinds of like this high performance software that you'll find. It's C++ stuff and C stuff. C stuff is usually written in a way that it can be accessed from whatever environment you have. So you just need to provide row pointers to row arrays that conform to that software's view of how it will use that array. That's how MKL works, and Atlas and such blast stuff. So they say, okay, give me a pointer to the array and give me some numbers, some strides or dimensions or so, and give me the pointer to the data. But C++ software often requires some data structures that are typical to that C++ software. So it's not really that easy to connect from Java. So Neanderthal can give you a free access to the C software, but not as the C++. It depends on how it's structured. But main I think for Clojure programmers, it's not so important, I think, because they usually are not so interested in writing low level C stuff and compiling into multiple platforms or so. They usually I think would like to say, okay, I have my REPL. Can I write high performance software from the REPL, from the Clojure environment? So the idea that I want to enable with Neanderthal is that you don't need TensorFlow. You don't need, I don't know, OpenCV. I mean, obviously, you need it because there is so much functionality there. But in ideal case, it would be, okay, my team has this wonderful idea. We have the algorithm. We know that that algorithm can compute some useful stuff. Now we have to write it. Can we write it from Clojure and don't worry about multi-platform build and C++ and C and everything else? Can we write it from Clojure and have a Clojure program that does it at full speed? So that's the main idea of Neanderthal. So I suppose if you need to use TensorFlow, you would need TensorFlow's, I don't know, Java interop library or so.
So, but in Neanderthal, the primitives are the Clojure data structures themselves, right? Or do you introduce different kind of primitives, like not even primitives, like the data structures that you use? If you say vectors, are they Clojure vectors, Clojure persistent vectors?
No.
Okay.
Because that doesn't make any sense.
Okay.
Why
just
matrices,
aren't they?
Why it doesn't have? For example, if you need high performant code, and you use Clojure vectors. Clojure vectors are like a bunch of references in Java virtual machine. So each number is not a primitive number. It's an object that wraps a primitive number, and it's scattered all over memory. So you don't have a guarantee that cache memory will be used in an optimal way. So what does it mean? It means that if you compute, like, if you have data about 1,000 workers and then they schedule and their managers and then what they do during the day, and you have to like write a software that provide like an information management software or so, it's quite fast for that kind of stuff. But most of the machine learning or linear algebra, these numerical algorithms, their complexity is not linear. It's usually quadratic complexity or like O of n to the power of 3 or even more. So basically, you need much more speed. You need to use cache memory in an optimal way. You need to use all these hardware, Intel's pipelining AVX instructions or whatever. So you cannot Clojure vectors and Java linked lists and Java array lists and everything else. It is really a bad tool for such kind of task. So what Neanderthal does, it practically maintains its own primitive like memory, and it enables you to look at it as a Clojure object, let's say. So you don't have to worry about low level stuff that much.
So all the functions that work on Clojure vectors, for example, they work on Neanderthal vectors as well.
Excuse me, I didn't understand that.
So all the functions that work on, so because Clojure abstraction is a sequence abstraction, right? The seek thing. So all the functions that we have that work on Clojure data structures, for example, Clojure vectors, they work on Neanderthal vectors as well. I mean, I'm thinking about like the user of this library. Then what should I be aware of?
So I suppose you mean like map.
Yeah.
Especially lazy sequence is a bad abstraction for high performance numerical stuff. So that's the point. Forget about it.
Okay, so we cannot use the same kind of things, but
but map as a concept and reduce as a concept is a good abstraction, even for numerical code. But unfortunately, Clojure maps and reduce are built in such a way to be not quite a good match for that. So basically, if you want to write a code with maps and reduces it, so you would use fluokitten. it's on one. It's
Yeah, so
one of my libraries.
that's where I was getting at slowly.
Oh yeah, okay.
Okay. Yeah.
So you would use Flow-Kitten, which offers
Yeah.
alternatives to MapReduce that are not only Neanderthal stuff. It's really a library that I had written before Neanderthal, like 4 years
Yeah.
ago. So it's like a category theory inspired software library that enables you these kinds of abstractions like fmap, freduce, fold,
Yeah.
operation, or so that are polymorphic. So if you call them on Clojure vectors, they will work with optimal algorithm for Clojure vectors. If you call them on Neanderthal data structure, they will call the appropriate optimized algorithm. So that's one of the combinations that you can use. But most often, I guess, my preferred combination is to use Neanderthal and matrix operations if they are appropriate for the algorithm. If not, to write my own with Clojure CL or Clojure CUDA. That's the best, I think. Yeah, Ray?
Yeah, quick question is, how does I mean, maybe it's just not possible, but have you thought about how these kind of things could fit into the transducer framework or the transducer model?
The thing is, I'm not sure whether it's even needed. Could you give me an example? What would you do with transducer and GPU function, or a Neanderthal vectorized function, or so?
Well, let's say you wanted to, put some data into, into a channel or something like that, and then you want to pull it off or put something onto a channel, but you want to have the results computed on the GPU, or a filter or a map on the GPU before you put it into a channel for further consumption downstream. Then it's quite nice to have that in a transducer, because then you could use it on a channel or on some other, on another type of input.
Yeah. And
that's a theory anyway. I'm just again, maybe I'm just in bullshit land here.
No, you're not. You're not. But what would be the shape of that data? Like, what's the size of that data? When you say data, it's like 10 numbers or 10 million numbers or 10 billion numbers.
Well, I think the idea is that it could be whatever you want, but then this MapReduce operation that you're talking about would do its work before it goes onto the channel. So the idea about, to me anyway, the idea about transducers is that you provide the algorithms, you provide the functions that do the operations on the data in a way which is orthogonal to the output channel.
Yeah, well, in that way, maybe, but I'm also maybe in bullshit land now. Also, so
you're on a different podcast. You're definitely in bullshit land.
Yeah. So the point is that may be orthogonal to Neanderthal. The point is, you would typically. So maybe now it's time to just make a short break, because I think we got into the quicksand now. Not with the channels, but I think that our conversation got a bit more stretched into details, so people would be bored. Maybe we could cut out this this first half an hour. So maybe we should speed this up.
Oh God, I hope not.
So the point is, let's say we will get back to this, but maybe we should look at it from a different perspective. Let's say you're a Clojure programmer, and I'm a Clojure programmer, and so you're not statistician. You don't have PhD in deep learning or whatever. So you know your programming. Perhaps you have some math courses in college that you forgot, more or less. Maybe you remember you remember some linear algebra.
Know us very well.
You remember, or I remember some linear algebra to the extent that there are such things as matrices, but you forgot even to what is eigenvalue or such things.
Eigenvector or yeah.
Yeah.
or so you recognize the stuff, but you forgot the details, and
Yeah.
so you don't have really idea how even to use this to any benefit. But machine learning is such a popular topic, so you recognize that you would love to learn it, at least some methods. You feel that you can solve some problems with it. Maybe your company have been gathering data for the last 5 years, and now and hoping then someday that data will answer some useful questions, but that day just is not coming. so so all of you are like creating some user groups and trying to learn those machine learning techniques, and you start reading blogs, looking at demos, like trying some software, and like you understand what those demos do, but you still don't understand how they do this. And okay, they have these pictures, and they teach their software to recognize like cows and hot dogs and not hot dogs, such stuff. But now my company has data about visa transactions and like vegetarian food sales in Amsterdam or so, right? So how can we use
This is
this?
perfect data.
So you realize that you need to dig deeper into machine learning theory, let's say. So you browse for books, and then you pick some popular textbooks, right?
Yeah.
So you're following me? You're in the same situations or not?
Definitely. We haven't picked the books yet, but
Yeah, but
go for it.
but you're on the Amazon and trying to build a wish list. Yeah.
I have
I'm looking right now. Yeah.
Yeah. Okay. So
I have
so
just started ISLR now, so
Yeah.
I'm in the next step.
yeah. So basically, you recognize that it's important, but you cannot. You still it's an alien land, and when you open these textbooks, you won't find any loops, any functions, any transducers or reducers or Java array lists or anything.
Right.
What you'll find there is a bunch of mathematical symbols, and most of them are matrix notations. So they will say, okay, you have this vector, and then you multiply this vector with the transpose of that other vector, and you get a matrix. And then you solve this matrix and find some other matrix, and then you plug this matrix into some other computation that we describe only in matrix notation, and only to a bit. We don't get into implementation details, and then magically this is the solution. So basically they give you some nuts and bolts, and they give you the details, but only on the level of linear algebra. So if you want to implement it, there are two possibilities. Either you understand this stuff that they talk about really perfectly, and you're a programming wizard, and you write your own loops, and you basically re-implement this matrix implementation from scratch. Of course, in reality, you won't get very far with it. Or you learn some matrix software library that will at least enable you to do some percentage of this stuff directly, and the rest you will have to write yourself, or to use a library that some other people wrote. So that's the point. For example, of Neanderthal.
Yeah.
You would love to get into the area, but all the literature is really either geared towards complete theory or applied theory, but applied to the level of matrix computations. So you need to know how to run and use matrix computations, and Neanderthal enables you like to recognize when you see the some combination of matrices in a formula in the book, you will recognize, oh, this is the matrix multiplication, and this is linear algebra, like solving the system of linear equations, and this is finding eigenvalues, and this is finding eigenvectors, and then these eigenvectors unplug it into this algorithm or so. You will still have to write something yourself, but only some part of it. And the point is, even those parts that you will have to write yourself, you would need speed. And you will get this speed through Clojure CUDA and Clojure CL most of the time. So that's the point.
You also have a statistics library, right? The Bayadera
Yeah, Bayadera.
Yeah.
Bayadera. And if you're curious about the name, why it's called Bayadera, some people in Germany recognize it because they went to the seas, to the Adriatic Sea. In ex-Yugoslavia, there was a cookie, really good cookie, some nougat cookie called Bayadera. It was really a popular cookie, which is called Bayadera.
Okay.
So it was nice, and it's also have something similar to Bayes. So that's why it's good. So Bayadera is quite interesting to me, and I think it's quite interesting even to the wider audience, because once the source repository on GitHub without any documentation got into the front page of Hacker News, and it got some hundreds of stars even without anything else. What's good with Bayadera? It's much faster than state-of-the-art tools. So state-of-the-art is basically Stan. It's a C++ Bayesian inference engine that has an R like front end. So basically, you will write some model in Stan's proprietary language and call it from R to do some Bayesian inference for you. Bayadera enables you to do a similar thing from Clojure, but your computation would run on the GPU. And we'll run, instead of, like, let's say 5 minutes, it will run in 300 milliseconds. And I translated a year ago. I translated most of the examples from the best textbooks in this area, like doing Bayesian data analysis, which is really a great resource for learning Bayesian and probabilistic stuff. It's written by a biologist with real examples, not some hello worldish stuff, but real examples from real scientific, like hypothesis testing or so. So really a great book if you want to go into this area. I suppose for most Clojure programmers it wouldn't be that interesting because they haven't decided to go Bayesian yet, I suppose. But if you want to go into machine learning, it's something you have to learn in statistics and probabilities and probabilistic way of thinking. And so you will come to Bayadera sooner or later if you want to create your own stuff.
So maybe you could write an algorithm about what the probability of a Clojure programmer coming to Bayadera is.
Definitely. Definitely.
So
that could be a good example.
It's an easy problem. It's an easy problem.
Awesome.
You don't need GPU for that, probably.
Yeah, you don't even need GPU. But the point is, Bayadera is a good example of how to use Neanderthal and Clojure CL and Clojure CUDA. So if you need some, for example, if you want to start and like go through some tutorials and then wonder, okay, but how do I do this exotic? How do I transfer this data? And then how do I call some complicated kernel on the GPU? You can browse Bayadera source and see how I did it with Bayadera and get some idea how you would do it for your own algorithm.
So for the people who want to get into this GPU stuff, so if I understand correctly, the first point of entry would be the Neanderthal. Yeah, no problem.
At first, well, if you want to learn only GPU programming as such, like
Yeah.
low-level GPU
Yeah.
programming, the point of entry would be Clojure CL or Clojure
Okay.
CUDA.
It's a low level.
And
Yeah.
and I place a great importance on helping people to learn it.
Mm.
That's why for all these libraries I provide. I usually pick up a textbook
Yeah.
and I choose some good one, like not really the simplest one, not really the like only for PhDs, but I choose some good textbook that would get you from beginner to intermediate, let's say.
Mm. Yeah.
And then I write examples, usually in form of tests.
Mm.
So I write the examples of how to use this library, and usually these examples are translation from the book examples. So basically, for example, if you want to learn Clojure CL and do some GPU computing, you would pick up Clojure CL in Action book from Manning. It's really good, from Matt Scarpino, I think is the author. It's really great book in the tradition of all the Manning books. That is really good match between getting you started and giving you really in action stuff, not only just some hypothetical examples. And Math gives a good a good batch of examples that gets you from the simplest Hello World ones to some more complex ones. And most of these examples, at least those that make sense with Clojure CL, are in Clojure CL's test folder. So I haven't written like blog posts with narration, but you can follow the book and look at the examples in Clojure and see, okay, this is how it's done in the book. Okay, how can I do this in Clojure? So you will get the explanation from the book, and then you will get the code from the tests.
Okay. So what's your future plans for these things? So you have CUDA, which is for NVIDIA things, and you have obviously support for AMD GPUs as well. So where are you taking these libraries to?
In the, let's say like this, the first steps now will be to give some more functionality to Neanderthal. It's not, I don't need it immediately, but I need, these are important to show that the library is more or less featureful and complete, and that people can rely on it. So I'll during July and maybe August, I will implement lots of new data structure for sparse matrices, like banded matrices, symmetrical matrices. Some of it I already implemented, haven't checked to the GitHub yet, but it's on my machine. I will not put proper sparse matrices. This is from the next phase, but I will try to probably cover what Blast and Lapak covers. That's the first part. The next steps would be to bring Bayadera to the level that can be used by let's say average Clojure programmers, because now I wrote Bayadera with Clojure CL and optimize it for the AMD GPUs, and most people don't have that. Most people usually have CUDA GPUs. So I will probably also write port whatever is there to CUDA also. I will try to polish it a bit more, write documentation, and start writing some more tutorials. So I probably try to keep some pace of about maybe 1 or 2 tutorials a month, sometimes even 3 or 4, but let's say 2 a month. And try to help Clojure programmers like get up on their feet with this stuff. So I hope these basic linear algebra stuff was received quite well. I think it has something like 20,000 readers in the last month.
Yeah.
Thanks to all for getting to the front page of the Hacker News, of course. But it was received quite well. So I can see that people like recognize that this is useful for them. So I'll probably keep writing those stuff, and I'll keep like getting more functionality to it. And I hope that because maybe I will introduce more bugs, because I recognize that most people are like quiet before, because there are many people that use these libraries, and when I ask them, okay, you're quiet, I haven't heard from you.
Because
do
it's
you
working
use it?
fine.
Does it work? No, it's working great. So I'll probably need to introduce more bugs to get people to complain more, and just show that there is activity in these projects.
Or maybe what you can do is every time they do a matrix computation, it's going to post a question to Stack Overflow automatically, and then it answers.
Yeah. So
Anyway,
and maybe I'll try to convince Vijay to try these libraries, so he can complain or talk about
of course,
it more.
Ouch.
Yes, I'll start doing that. But by the way, are you going to be at Euroclosure?
Excuse me, I have some problems in connectivity.
Are you going to be at Euroclosure?
Unfortunately not.
Oh no.
I mean, my talk wasn't accepted.
Yeah.
But fortunately, 2 talks would have some stuff about Neanderthal and Clojure CL. So maybe they picked another talks, and I think it's better, because instead of me just saying how Neanderthal is great, other people will say how Neanderthal is great. So I think it's better for the visibility and for convincing people to try to use this stuff.
Yeah, that's true.
So basically, it's not rocket science. You can use it.
Yeah.
If you're a Clojure developer, you are ready to use Neanderthal.
So I think we are almost at the end of the almost at 1 hour. So I think we can wrap it up. Just to I think one of course we're going to be at Euroclosure. Ray is going to be there, and Ray will be there, and I'll be there as well. And first, I'd like to give a quick shout out to Cognitect, because they gave us one free ticket to attend. So thanks to Cognitect, guys, and Lynn and Alex Miller, of course. And I think now we can roll the credits. And Dragan, thanks a lot for joining us and giving us the insight into what you're building and the high performance side of Clojure. And hopefully we'll meet you at Euroclosure. You'll be attending there, right?
No,
not even attending.
As I said, I don't have a talk, so basically, I don't have. I'm interested in listening, but well, my funding can only cover if I have a talk. So know how it's at university. You have to have a talk to be able to attend. So unfortunately, I won't be able to attend.
But we'll go there and then spread the word. So
yeah, thank you very much. I can see I put you to sleep. So
no, that's not
at all. No, it's definitely some challenging stuff, though. I think, like you say, the ability for us to get Clojure developers onto the kind of the linear algebra way is still coming, but I think you're doing great work in this area. Without this kind of stuff, then we've got no chance. Because if we just rely upon the JVM libraries or integration with Python or R, then people won't do interesting things in the Clojure world. And I think this is the real key important thing that you're bringing here.
Yeah. The key thing is that enable people to create stuff in Clojure that is not available on other platforms. So basically, not to just follow what is out there. But to try to create some killer app.
Okay.
Yeah, excellent stuff. Yeah, thanks a lot.
It's the time to roll the credits.
Yeah, thank you for inviting me.
Yeah, thank you for joining us. And as I said, we'll try to spread the word around Euroclosure, and hopefully we'll see you again. And I'll certainly give it a try to see what I can do, especially have the CUDA thing now, because as you know, on a Mac, I have an NVIDIA stuff. So I'll give it a try and I'll poke you, and maybe I'll be the guy who'll be posting stupid questions on Stack Overflow and
Yeah, just complain as much as you like. I will try to help you.
Thank you.
Okay, I just before you go, are you going to? We've got links to kind of your GitHub and all this kind of stuff, but you said you can recommend some books as well for people like me who are just getting into this stuff and good beginning material. So maybe I can take a few months over the summer and then come back in the autumn with some questions.
What would you like to learn?
Well, you mentioned you have some books about the machine learning Bayesian stuff.
Okay, so for Bayesian stuff, I would recommend doing Bayesian Data Analysis, second edition by John Kruschke. Also, for like old school machine learning overview, there are two good books. One is Pattern Recognition and Machine Learning from Christopher Bishop, who is, I think, a researcher at Microsoft now or something like that. He's also a professor in USA. And there is also by, I think, Kevin Murphy, Probabilistic Machine Learning by MIT Press. These are three books that are like covers you with data analysis and also machine learning stuff. But before that, I would definitely recommend some linear algebra refreshment. And I recommended this book called, I think linear algebra something. You have it on my blog because it was a really good choice because the most important stuff when you pick a linear algebra book is to pick one for engineers, not one for mathematicians.
Right. Yes.
So this one is for engineers, and it was like $1 on secondhand on Amazon. But when I recommended it now, it's like $40 or something like that. So maybe you can choose another one.
Can you recommend a cryptocurrency as well? But we'll hold this back before we we release this program. We'll hold. Just tell us. Is it Ethereum? Come on, tell us.
No, I can recommend you, but I'm not a believer in cryptocurrencies, and I don't know anything about that. So
I think. What he's going to recommend is Dragan coins.
I recommend Dogecoin.
Coins. Okay. Yeah, right. I thought you were going to come up with your own cryptocurrency, that is going to be mined by Neanderthals secretly. Every time somebody uses the library, you get a coin.
Yeah, and like veg cryptocurrency.
Exactly.
We call it veg coin.
Yeah. Veg coin, yeah. But it's not only coin; it's like a veg ether or something like that for some like buzzwordy computation on the internet.
Maybe we call it Vegium.
Vegium,
yeah. Anyway, so on that bombshell.
You heard it here first, folks.
and instead of Satoshi Nakamoto, you will get Ray and Vijay.
Exactly, and then we keep getting the coins.
We'll have to go into hiding pretty quickly.
we have practically retired because of this podcast, by the way. So that we can't do anything else. That's what I mean. It's not that we can retire.
Yeah, well, just mention like globalization, Trump, Putin, and usual buzzwords, and I think listeners will skyrocket. Like all the audience will be in millions.
I don't think people are appreciating that much, but anyway. So I think that's pretty much it for this week, and
all right. Cool.
Hopefully, we will release this before you'll be. I don't know, the people who are listening to this one. Most probably, you folks will be listening it before Euroclosure, and we will be there at Euroclosure with some Defen stickers, and Ray and I will be there as well. So please stop by and say hi. And if you want to punch us, please punch Ray.
Yeah, I'm going to be doing hopefully a little unsession there as well with functional programming jokes.
Yeah.
But I've got to get a bit of love on the GitHub page, so I'll put a link to that in the show notes as well. So
so the more reasons to come and punch Ray. So please,
many more reasons.
Yeah,
please join us there.
Ray, please tell at least one joke about Neanderthals. So
Right.
So,
evolution
request.
of programming.
Yeah.
Special request. Okay. Cool. So that's it for the show. And let's roll the credits. First of all, I would like to thank Dragan again. Thank you for joining the show and taking the time on a Sunday evening, spending time with us, and also going outside and then buying a headphone, especially for the podcast. So
Yes,
that's a lot of commitment.
That's a first.
Exactly. And our sound engineer who is fixing all our voices, Mr. Wouter Dullard. I don't know if I don't pronounce it properly. He said he's going to replace it with proper pronunciation. And our music is done by Pizzeri. So please go and listen to those music. The music tracks on SoundCloud. The links will be in our doobly-doo thingy or the show notes somewhere at defen.audio. So that's it from us for this week. Ray, any closing thoughts?
No, I think it was just really good. Thanks again, Dragan. It was really an amazing little dive, even though it was in warm waters, into the pool of linear algebra and matrix maths and all this kind of stuff. So thanks again for doing all the good work, and hopefully we can bring a few more people into the library because of this podcast, and I'll definitely try and make a few jokes about it. Yeah.
Okay.
Thanks very much.
Yeah. Thanks for
Bye-bye.
calling me and inviting me. Bye-bye.
Bye.
How do you stop this?
There's a red button.